Welcome back. Next up, we have Hannah Lee. She got her PhD at Stanford in operations research. She's currently doing a postdoc at MIT before she starts in Columbia Business School next year. She's an expert in inference, external design, and online marketplaces, in particular in the presence of interference between making different experiments and treatments. So take it away.
Awesome. Thanks for the intro. All right, so the work that I'm going to be talking about today is kind of a collection of different results from 3 pieces of work that I've worked on during my PhD, and I'll try to focus on some of the newer ongoing work. And this is work with my PhD advisors, Ramesh Johari and Gabriel Weintraub. So let's talk about platforms and decision-making. So if you're a platform, say something like Airbnb, you have countless choices in how to design your platform. How many listings are each customer going to see? How are listings going to be highlighted? What kind of pricing fee structures are each side of the market going to engage in? Things like that. And how do platforms tackle these problems? Well, a lot of what they do, they rely on experimentation. It's also called A/B tests, or depending on different fields, randomized controlled trials. So to go through an example, let's say that Airbnb, a lodging platform, is considering a new intervention where they want to show higher quality listing photos to the customers. Before they decide to introduce this to everyone, they want to know how it affects metrics that they care about. And a metric that they care about could be, do the number of bookings increase on the market? The goal here is to estimate what we call this global treatment effect. So this is the difference in the metric that you care about between a world where everyone sees this intervention, everyone sees the nicer pictures, and a world where no one sees it. And what they'll do is they'll run an experiment. They'll give the intervention to some customers, not to others. So the treatment customers will see the better photos and the control customers won't. And then use the outcomes of the treatment control customers to estimate the global treatment effect. Typically, you'll just take the average of both the 2 groups and subtract them. And so there's a lot of advantages to making decisions this way. When you do this, you now have evidence for what decisions what kind of interventions you should enact. So this allows for data-driven, basically data-driven decision making. If you didn't have this experimentation, you might have to rely purely on intuition for deciding whether or not you should introduce something, or relying on what some people call HIPPO, relying on the highest paid person's opinion in the room. But this really allows us to actually use data in this decision-making process. So that's all well and good. But the issue is that in a lot of marketplace settings, you'll actually have biased estimates of your treatment effect. The estimates that you're getting from the experiment will be systematically biased from the true global treatment effect. And let me walk through briefly why this happens. And what you're going to see is that in these marketplace platforms, you have competition, you have economic competition that will then create interference and then biased estimates. So again, the estimate that you care about is this global treatment effect. And suppose that you introduce this customer-side experiment so that a control customer will see the old listing photos, and a treatment customer will actually see the new listing photos, but they might overlap in the listings that they see or interact with. And now, suppose that this treatment makes the treatment customer more likely to book than a control customer. Suppose that this treatment customer then books one of these listings, that listing then becomes unavailable for the control customer. And so what you did here is, by changing what the treatment customer sees, you're actually increasing the amount of competition for the control customer and reducing the supply available to them. And so in this experiment condition, they're actually facing more competition than they would have been in the global control world. And so these experimental outcomes for the control customer are actually not representative of a global control outcome. Because of this, you'll end up underestimating the amount of bookings by control customers, overestimating the bookings by treatment customers, and you'll end up overestimating the treatment effect in this case. And so more generally, whenever you change one customer's booking probability, you change the supply available for other customers. And whenever you change how attractive one listing looks, you change how other listings look in comparison. And so when you have constrained supply, constrained demand, this will create interference in your marketplace. All right, so where does the prior work stand in this topic? A lot of the prior work here so far is focused on these bias treatment effect estimates. And so specifically, there's been a couple recent works that have shown that the size of the bias can be quite large. People have found instances where the size of the bias is somewhere between 30% of the treatment effect to, in some cases, 230%. And so it is indeed a big problem. And this is something that's come to the attention of not only academics, but also industry practitioners. And a lot of these papers are done in collaboration with practitioners. All right. And so these platforms have started to realize that, yes, interference is an issue, this bias is an issue. And so they've started to adopt some methods to help reduce this treatment effect bias. The most common ones are cluster randomization and switchback testing. In some of our work, in our earlier work, we've introduced this two-sided randomization as well. And generally, there's a couple other topics as well that leverage the structure of this marketplace better to help reduce the bias. And so we also have some work. So this is from two previous papers, thinking about when the bias is large versus small. So if you look at some of these empirical papers that find, the size of the bias is between 30% to 230%, you might wonder, which case are you in? When is it bad? When is it not? And so in some of our work, we tackle this and we show that the size of the bias is heavily dependent on the amount of supply and demand imbalance in your marketplace, as well as the type of experiment that you're running. So I'm happy to talk about this later, but what I'm going to focus on in this talk actually is taking a step back from here and saying, yes, we know the treatment effect bias is there, but how does this ultimately affect the decisions that a platform makes from these experiments? And hopefully by the end of this talk, you'll see that there's more to this problem of how experiments affect decisions than just the treatment effect bias. And what I'll try to explain is that these interference effects in these marketplaces can actually create multiple types of biases. And in the presence of multiple biases, sometimes fixing just one bias can actually hurt the decisions that you're making. And so we'll take this a little higher level view of experiment design and decision making. So let me first go through how a platform uses experiments to make decisions in the first place. So a platform will run an experiment, and then they'll usually decide upfront some sort of significance level that they care about, alpha equals 0.05, and some sort of launch threshold C. You can think of this threshold as some sort of cost of launching this new intervention, where you say, if the benefit of launching these higher quality photos to the entire market is better than the cost, then we want to launch. Otherwise, we don't. So you run an experiment, and from the outcomes, you come to a point estimate of your global treatment effect. And then you estimate the standard error of this estimator, this global treatment effect estimator, trying to understand the distribution that it's coming from. From the standard error estimate, you then create your confidence interval. So in this case, it would be a 95% confidence interval if alpha equals 0.05. And a simple decision heuristic that we'll use here is a heuristic where we say, if the confidence interval lies above this bound C or above this cost C, then we're going to launch. And so this is kind of one example of kind of a standard decision-making protocol that a platform would use. There are certainly more complicated ones as well. Sometimes platforms will look at several different metrics, and but this is kind of the core of this decision-making. And so to bring this back to where the current literature stands, well, interference can actually create multiple errors along this decision-making pipeline. Prior work has mostly focused on this first one here, this biased estimates of the treatment effect. But what we're going to do in this work is also talk about biases in the standard error estimates and then how these biases propagate to the confidence intervals and decisions that are made from it. So here, what we're going to do is we're going to define this dynamic marketplace model of a two-sided marketplace, and then use this model to study first what kind of biases arise in the standard error estimates, and then how do these biases in the standard error estimates and treatment effect estimates then affect our decisions. And similar to Anisha's talk, actually, this work is a little bit on the boundary between OR and more causal inference methods, where the types of questions here, experiments with interference, violations of SUPA, this is very much a causal inference problem. But the way we're going to address this is more through an OR modeling method, where we model a marketplace, come up with this basically a data generating process for the market, and then study how estimators perform in this model. So takeaways from this talk, the results that we find are that in a large class of interventions called positive interventions, which I'll define later, this treatment effect bias and standard error bias cause a platform to launch too often. There are interactions between these two biases, and sometimes fixing one bias can actually hurt your decisions. But we do provide a method to help reduce the standard error bias that also improves your decisions later on in the pipeline. All right, so that's the goal. And now I'll just jump straight into the model. What we're going to define is a continuous time Markov chain model of a two-sided market, where first you have customers. Customers can have different types. Types can represent, for example, an Airbnb, what location you want to buy from or how price sensitive you are. And different customers will arrive at different rates according to a Poisson arrival process. When they come, there's going to be some set of available listings on the platform. And customers will interact with these listings. So first, the customer will form some sort of consideration set. So you can think of this as, what does the customer even see on the platform as a result of search and recommendation systems? And here, each of these listings is considered, is included in the consideration set with some probability alpha. Alpha that can depend on both the customer and listing type. Oh, and listings can also have different types. This can represent things like number of bedrooms they have, location, things like that. Now, from this consideration process, the customer then makes a choice about whether or not to book a listing, and if so, which one. And this section is modeled using a multinomial logit model, where the customer can have different utilities for listings of different type, as well as some outside option. Now, say one of these listings is booked, that listing then becomes unavailable for some amount of time before it later replenishes. And the rate at which it replenishes is governed by this tau of theta parameter, which is also a function of the listing type. And so within this model, this is kind of a model of how the marketplace dynamics will move. This is actually a Markov chain model where the state of your system is the number of available listings at any given time. And so these arrival rates and replenishment rates will govern how the state transitions of your system. And again, this is a data generating process for the underlying market, but we don't assume that the platform actually knows any of this. What the platform does, though, is they run experiments on these users or on these listings. And there's two common types of experiments. We'll mostly focus on a customer side experiment in this talk. And so here, this is the same type of experiment as in the earlier motivating example, where customers are randomized into treatment and control. If they're in the treatment group, they see the shinier photos. If they're in the control group, they see the old photos. What that amounts to in the context of the model is this changes the utility that they have for a given listing. And then kind of the naive Horvitz-Thompson or Horvitz-Thompson estimator is this estimator given here, where you just take the number of treatment bookings normalized by the size of the treatment group minus the number of control bookings normalized. And since in our model, we consider the rate of the bookings So we normalize by time as well. You can also randomize on the other side of the market. We have some work on this about differences in the bias between these two types of experiments, but I largely won't go into that in this talk. The quantities, okay, so then once we have this Markov chain model, we're going to study how the system behaves in these three counterfactual worlds. In this world where everyone has this like new set of utilities, global treatment, or global control, or the experiment world. And our estimand, what we want to estimate is this global treatment effect, there we go, is this global treatment effect right here. So this is the steady state difference in the rate of bookings between the treatment group and the control group. And again, the estimator is just this time average from your observed bookings. Something else that we'll want to know about our estimator is the standard error. And the standard error is just defined to be the standard deviation of the GTE hat sampling distribution. All right. And so this is how we're going to analyze these experiments. And now we're going to go through each of these steps in this decision-making pipeline and kind of figure out what happens in each one, what goes wrong, and how can we fix that. So first, we have this point estimate in your treatment effect. And so again, a lot of prior work is focused on this specific step. So things about like looking at the size of this bias, work that we have looking at like how the size of the bias depends on supply and demand imbalance, that all falls into this one. But the takeaway for this step for now is first, we're going to focus on a certain class of interventions. This class of interventions is something that we're going to call positive interventions. These are interventions that will increase all customers' utilities for the listings in the platform. This doesn't have to be a uniform increase. People can still have heterogeneous treatment effects, but what I'm saying is I'm ruling out the case where this treatment makes some people like the listing more and makes other people like the listing less. Examples of such interventions could be things like these higher quality photos or maybe discount codes, which everyone would like, potentially to different amounts. But in this setting, what we prove is that in a positive intervention, these naive estimates, customer side or listing side experiments, they will overestimate the magnitude of a treatment effect. And yeah, so this, I'll have you keep this in mind, but I'll largely move to this next step, and we'll come back to this in a couple of minutes. All right, so now what's been less studied so far is what are the estimates in the standard error? And it turns out that, so again, finding the standard error, it turns out that in these marketplace settings, if you do the naive standard error estimates, you'll again get biased estimates. And what happens here is that how platforms typically do is that they'll assume that all individuals are independent, which again, like I said, because there's interference, this isn't true. And so this will create biased estimates. And here, this is a plot from our simulation showing what would happen in a marketplace. What does the bias look like as a function of, on the x-axis, the time horizon of the experiment. And here, this is these are calibrated simulations to some like real two-sided marketplaces. And one thing that we find is that here, when the time horizon is shorter for an experiment, you actually have much worse bias. And the size of your standard error bias is roughly around 30% the size of the actual standard error. But as this experiment runs for a longer time, the relative size of your standard error or of the bias will actually decrease. And so what's happening here? Why does it look like this? And also like note in particular that here we're always underestimating the true standard error. So that's saying when I'm always like thinking I'm more confident in my estimate than I truly am. And so what's happening here? Well, basically what we're looking at is we're looking at the variance of this expression, this number of treatment bookings minus number of control bookings, which is the sum of the variance of the treatment bookings plus the sum of the control bookings minus the covariance between these two groups. And in naive, the typical standard error estimates that platforms run, they'll just completely ignore this. They'll say that everyone's independent and ignore that last term. However, there is a strong covariance. There is a strong correlation between the number of treatment bookings and the number of control bookings. So again, here we can see that as this is the behavior of the covariance, and it follows a very similar pattern as the standard error bias, where there's a much higher covariance, scaled covariance, when you have a shorter experiment and much less covariance correlation when you have a longer time horizon. And so what's happening here is that, again, there's a competition between the treatment control customers. When treatment customers book more listings, there's less available for the control. And so you have this negative correlation there that will then lead you to underestimate your variance.
So can you give us a sense of the time scale? So 10 is compared to how many units of inventory we're talking about here? Or how many units of experimentation?
Yeah, so that's a good question. This depends on a lot of parameters. So I think in the calibrated settings that we found, I think it corresponds to something more like in this range here, where you have a 10% bias. But this definitely depends on how long the experiments are actually running, what's your minimum detectable effect that you're aiming for. So it depends on a lot of things like that.
Is this issue different from, say, some of the methods in econometrics for clustering standard errors and trying to have robust standard errors? Would that address this type of issue? Is this issue of a different nature?
Yeah, so there is the issue of for clustering, there are different types of customers or different types of listings, and there are heterogeneous variants or standard errors differences as well. A lot of that would be addressed by the clustering. But in addition to that, you have this interference effects, where when one customer goes to time 1, this affects the customer at time 2, which affects the customer at time 3, and a lot of that is not isn't addressed, as far as I know, by some of those methods.
Because we could try to think of those customers as pertaining to the same time bucket and cluster with that time bucket. If they're like booking around the same time, I don't know if that. Yeah.
So actually, that is pretty similar to some methods that we take. Yeah, so maybe I'll talk about how we discuss. I'll talk about how we address this, and I think there is a lot of intuition that uses the same idea. Yeah, so to sum up in this talk, just like what we saw in the treatment effect bias, in the treatment effect estimates, we see the same effects happening in standard error estimates, where the fact that there's competition in this marketplace is creating interference and then bias. All right, so given this, how do you reduce the standard error bias? One thing is when we look at this earlier plot, we see that the size of the bias seems to be decreasing the time horizon. So a very simple proposal is just to run a longer experiment here. And indeed, we show that for a customer side experiment, as we increase the time horizon, the size of the bias approaches 0 for the standard error. And what's happening here is very similar to the intuition presented earlier. It's this idea that as a customer, you're probably affected by the customer who came just before you and maybe the ones just before them, but you're probably not affected by a customer who came, a week ago or a month ago or a year ago. And so there's probably some limit on the amount of customers who are actually affecting you. And so as you're increasing the length of the time horizon of the experiment, for any individual customer, you're going to be less influenced by a larger proportion of the customers. What this means in a mathematical language, so what we end up showing is that this system is a regenerative process. So this Markov chain is a regenerative process, and you can actually think of this Markov chain as consisting of independent chunks in time. And these chunks are defined by when the Markov chain hits a certain state of the system again. So for example, say there are 100 listings in the market, and it replenishes whenever you hit 100. If I'm coming to the market, sorry, if I'm a customer and I'm coming to the market and I see 100 available listings, I'm not affected by whoever came just before that. And so there's these limits, you as a customer are only affected by people who came in the same chunk or block as you, and you're independent of everyone else. And so when you're on this longer time horizon, you get less bias in your standard error. We also have a second method for reducing the standard error bias, because in this first method, well, you don't always want to have to run longer experiments. There are opportunity costs to doing so. Sometimes it's just not feasible. So within a fixed time horizon, how can you reduce standard error bias? Well, here, the method that we propose using is what's called a time series block bootstrap method. And so I won't spend too much time on this, but for standard bootstrap methods, what you'll do is you'll resample individuals from your population. And then from these resampled individuals, you'll calculate things that you're interested in. You'll calculate quantities that you're interested in, repeat this multiple times, and get some sort of estimate of how much you can differ here. What we're going to do here, though, is we're going to use a bootstrap technique that's modified for time series data in particular, that really captures this local interference, the fact that you as a customer are also influenced by the customers who came in a nearby time. And so what we do here is we have resampled blocks from this time series. And we create like a pseudo time series. So from this observed time series, what we're going to do is sample a block of some fixed length k, and then we're going to append that to our pseudo time series, and then sample another block, append that to our time series, and then keep doing this until we get a new pseudo time series of the same length as the original. And so from each of these bootstrap runs, this gives you some new pseudo time series from which you can calculate this treatment effect estimator. Now you repeat this capital B times, and then you'll have capital B number of these like treatment estimators, and you calculate the standard deviation of them. And this gives you the bootstrap, this time series bootstrap estimate of your standard error. All right, so how does this perform? We show that in a number of different settings. For a customer side experiment, the bootstrap standard error estimation has actually less bias than the naive standard error estimate, both for customer side experiments, and also for listing side experiments, which we largely didn't get into today, but it has benefits for both. There's a caveat though. So yes, this time series bootstrapping method can help mitigate this bias, but there is a caveat where you do need to tune the block lengths that you're sampling. So again, what I've kind of said is that, yes, in this regenerative process, you're bounded by, you're kind of bounded in the time, basically the number of customers who affect you. They have to be in the same immediate chunk, but these block lengths have to be long enough to capture the dynamics in each of these blocks, in each of these chunks. And you as a platform might not know that up front. And so there is some tuning that you have to do here to get better performance. So this is like, this is still ongoing work. All right, so now I've talked about bias estimates in your standard error and in your treatment effect bias. And then both of these will come together to affect the coverage of your confidence intervals. I won't really spend too much time on this, but basically when you have this treatment effect bias, it's shifting your confidence intervals right or left. And when you have these standard error biases, it's either decreasing or increasing the width of your confidence intervals more or less than they should be. And so this will create errors in your standard in your coverage. And we actually do characterize the asymptotic coverage of the confidence intervals as a function of the treatment effect bias, standard error bias, and true standard error. So like skip over that and largely just talk about how this influences the decisions that you as a platform are going to make. And so recall that our goal in these settings is to launch this new intervention whenever the treatment effect is larger than the cost. And the decision heuristic that we're using is we're going to launch if this confidence interval lies above that cost threshold. And we're going to evaluate our decisions. Our decision is correct if we launch if and only if the true treatment effect is larger than the cost. And so here you can kind of have two errors that you can make with these decisions: a false positive launch decision where you are launching the intervention, but you shouldn't be, where the true treatment effect is less than the cost, but you think it's more than the cost. You can also have a false negative error where you are saying that this treatment, which is actually good, you don't think it's good, I'm not going to launch it. All right, and so now let's go back to this class of interventions that we talked about earlier, the set of positive interventions. These are interventions that basically help everyone. And so here, what we see is that, again, we're overestimating the size of the treatment effect in our experiments. And so this is going to be shifting your confidence intervals to the right. And we're underestimating the true standard error here. If you put this together, what does this mean in terms of decisions? Well, we're going to systematically bias our estimates upward. And so we're going to think that our treatment effects are better than they are. And we're going to be more confident in our decisions than we really should be. And so this is leading us to this is going to lead us to actually over launch more often. There are a lot of settings where you shouldn't be launching this new intervention, but you are. So then how do the methods that we proposed earlier of reducing the standard error bias, how do they impact these decisions? It turns out that fixing these biases doesn't necessarily equate to improving the decisions that you're making. And so we'll start with, this first method of reducing the standard error, where you just run a longer experiment. If you run a longer experiment, you can see as you increase the time horizon, then your standard error bias is decreasing, which is good. That's what we wanted. However, if you look, so again, consider a scenario where the treatment effect is actually less than the cost. Here, anytime you decide to launch, that's a false positive. And in this scenario, if you look at the proportion of false positive launches, this is actually increasing in the time horizon, which is bad. So now it's like the longer experiments that we run, the worse decisions we're making, which you certainly don't want. What's happening here is that as you're running these longer time horizon experiments, the actual standard error of your estimates will be decreasing together with the standard error bias. And so now we'll be increasingly confident on the size of, we'll be increasingly confident on our biased treatment effect estimates, and we'll be launching more often. So this is also kind of an illustration of how this idea of interference is not something that can be fixed by having more data. And in this case, when you have more data, more observations, you're actually making worse decisions. Well, I promised earlier that we do have some method that would help improve decisions. And so we turn to the second method that we proposed, this reducing the standard error bias using this block bootstrap technique. And here, considering the same scenario, we find that this bootstrap method actually reduces the standard error bias and also reduces this false positive launches. And so here in this plot, I'm showing on the y-axis the number of false positive launches. So the higher the bar, the worse decisions you're making. This blue bar here is what happens when you just use your naive standard error estimate. And then in this red bar here, we're showing what happens when you replace that standard error estimate with your bootstrap standard error. And so here we're having much fewer false positive launches. So we're doing much better in terms of decision making. And this third bar here, this green bar, is what happens when you run a longer experiment. So this is the other method of reducing standard error estimates. This here actually increases the number of bad decisions that you're making. And so we've tested this in several different parameter regimes, both in regimes where you have a lot more supply than demand, in settings where you have roughly equal amounts of supply and demand, and in settings where you have a lot more demand than supply. And we see similar patterns across these regimes, where this bootstrap method does improve the false positive launches, does decrease the false positive launches. However, this just running a longer experiment does not. And so this is kind of all just to say that if what you care about is making better decisions, you do have to be thoughtful about the errors, the fact that there are multiple types of errors in your platform, in your experiment, and how you address these errors. It's possible to fix some errors, get worse decisions, but it's also possible to fix the errors and get better decisions. So there are a lot of interactions there. Now to just sum up, what we show is that both the treatment effect estimates and standard error estimates will interact with each other, create incorrect decisions. We propose two methods of reducing the standard error bias. One of which is running these longer experiments, which worsen with decisions. The other is using this block bootstrap technique, this time series bootstrap technique, which actually improves the decisions in the cases that we study. And so, yeah, there's basically a lot more to look at than just the treatment effect biases that a lot of the current literature is focused on. There's a lot more happening around these experiments. So as open questions, one thing you might ask is, what happens when we combine these standard error bias reduction methods with the treatment effect bias reduction methods that are already in the literature, things like cluster randomization, switchback testing, or things that leverage different structures in the marketplace. What happens with the decisions once we do that? And in general, also just more study on the resulting decisions that we're making from these experiments, and also how these platforms are using these experiments to begin with. So oftentimes platforms have very structured methods of implementing these experiments. Sometimes they'll do ramp up experiments where you introduce this intervention to 1% of your customers. Then if it looks okay, you ramp it up to 10%. If it looks promising, you keep ramping it up. Well, in that context, how does interference affect the decisions that you're making there? How do these different types of biases affect these decisions? Platforms are also running all kinds of simultaneous experiments and making decisions from there about what experiments to run next. So basically taking a little more of a high level view about how platforms use these experiments and how this usage is affected by interference or different statistical methods underlying them. So with that, I will wrap up and take time for questions.
Do you have a false negative?
Yes, yeah, so this is a really good question because yes, basically I gloss over that, kind of swept that under the rug. There's a lot more to be done here in basically evaluating how good our decisions are, because sure, I could reduce my false positives by never launching ever. But then that would of course reduce your false negatives. So we see that in these scenarios, we actually don't increase the false negatives, although I will say right now, we're definitely looking for a better metric just in terms of how to evaluate the decisions that we're outputting.
Just to try to clarify, so if we use the block bootstrapping, but we still increase the time horizon, eventually it will make the decision worse, right?
Yes.
Because it reduces the bias of the.
Yeah, because then your standard error would still be getting smaller and smaller. And then you'd still be more confident about your biases. Yeah.
Give me a sense of why do you need to stick attention to positive interventions? So if there were some types that were negatively affected, how that changed things?
Yes.
Hannah, can you repeat the question? Can you repeat the question?
Sure, yes. So I asked about positive interventions. Why is it important to use intervention? Positive interventions. Maybe there are some types of customers that would be affected negatively.
Yeah, so if there are if there's an intervention where some customers didn't like it more, other customers like it less, you'll still have the same interference structures. And like this, the competition will still be there. What you don't have guarantees on then is whether you're overestimating a treatment effect or underestimating. And so there, it could be possible that there are edge cases where you actually end up underestimating the treatment effect, even when the treatment effect is positive, things like that. And so like a lot of our results actually in the paper do extend to it, or various papers do extend to more general settings like that. Things where I said like the size of the bias depends on your supply and demand imbalance. Those all hold, but this overestimation does not. And really here I focus on this setting where you overestimate because it's a little bit more clean to look at how the decisions are affected. When you can potentially overestimate or underestimate and your standard error estimates are too narrow, it's not clear what kind of errors that will be occurring there in terms of decisions.
If you are trying to figure out whether an intervention is positive or negative, could the bias in GTP be helpful?
Yes. Yes. Okay. So I think what this question is also saying is like, suppose there's no cost to launching. We just want to know if it's positive or negative. And so here, yeah, if the treatment effect is negative, then you'll just have you'll overestimate the magnitude, and treatment effect will be even more negative. And so yeah, that's actually helping you if your sole if the goal is just to determine positive or negative. And that's actually equivalent to even the decision-making case when you have no cost to launch a product and you only care about if it's positive or negative. Yeah. And yeah, so here we really are sensitive to, do you care about the cost or do you strictly care about just the sign?
Some proof that there is any kind of history dependence, because in what in the example you could see that a house of 5 reviews is not going to look like a house of 1,000 reviews. And as you go through, the choice is actually going to be history dependent. So we break the assumption that somebody far behind is independent.
Sorry, if this will do better when there's in person support.
So, someone that the inform is irrelevant. But if there is some sort of history dependence in your choice or in your marketplace, say I actually see the number of stars that the place accumulated, there will be some history dependence. So by assuming that away, are you doing something bad? Are you doing something good?
Oh, that's an interesting question. Yeah, so here, like the implicit assumption that I've been making is that a customer's behavior is only a function of the current available listings. And what you're saying is, what if it's a function of the current available listings and also some parameter like the ratings of that listing? To be honest, I haven't thought about that. That certainly makes it more complicated. You could imagine scenarios where okay, I won't posit, I won't just theorize right now, but it's certainly more complicated, and I'm happy to talk offline.
All right, let's thank the speaker again. Now we have a reception, 5:45.